So, we are now in the borderline of jumping into advanced mathematics, into advanced analysis. The calculus was also advanced mathematics, but we are advancing further. So, what we are getting into is an advanced version of calculus, where much more detailed analysis is being done with the problems, and this leads to a subject called real analysis. Real analysis is one of the most beautiful, one of the most fantastically crafted subjects of mathematics, and its effect and its immense influence on mathematics is clear. There is hardly a subject, especially if you talk of applications, there is hardly a subject which can do without real analysis, whether it is economics, whether it is physics, whether it is say optimization, whatever you want to say. Mathematical analysis plays the key role. And one of the most fundamental concepts of mathematics, in fact, I would say, not just mathematical analysis, is the notion of sequences. A sequence is a function f from a natural number set n to R, a real number set. So, f from n to R. So, how do you represent the sequence? So, the sequence is represented in the following way. So, we will do it in a tabular form. So, here is n, which is belonging to capital N, which is nothing but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, just go on. And this is f of n, which traditionally world over the symbol has been taken as xn. I of course do not know the reason why they have done so, but it is used. So, it is very difficult to say reasons. I think there is some book on the history of mathematical symbols. So, I can tell you later on, but I do not remember it right away. Now, so put n is 1, 2, 3, 4, 5, 6. So, here you have x1, x2, x3, x4, x5, x6 and so on. So, some of these values can be repeated. So, it is when you write a sequence, it is actually a complete tabulation of the function values, right. So, usually a sequence is given as or written as not given as, written as xn, wherein some people also write like this, or so n equal to 1 it is x1, n equal to 2 it is x2. So, it is a shorthand of writing. So, it is actually complete enumeration, right. It is not the standard way you write functions, please understand, because if you want to write the range of the functions, you take away the repeated values. So, it is a complete enumeration. Complete enumeration means exactly doing this, writing down it in the tabular form. So, for example, if I take the sequence f of n as 1 by n, so the sequence xn now, so we will not write n equal to 1 to infinity, we will just write this, it is obvious, is 1 when n is 1, is half when n is 2, is 1/3, 1/4, sorry 1/n, it just goes on without end. So, this is the complete enumeration, right. For example, let me tell you another sequence. So, in this case, what is my sequence xn? Sequence xn is the following: when n is 1, it is minus 1, when n is 2, it is 1, so n is 3, it is minus 1, so it is minus 1 plus 1 minus 1 plus 1 and it just goes on. So, you cannot write that this sequence is minus 1 plus 1, the range of this sequence is minus 1 plus 1, the second sequence, but the sequence always has to be represented in a completely this particular tabular form. So, let me put for example this sequence. Here also you see there is no repetition, here there is repetition, here also for example this sequence has no repetition. So, if I say, so basically we are just squaring the numbers 1, 4, in case of 3 it is 9, in case of 4 it is 16, it's 25 and so on and so forth. Every sequence, the cardinality of every sequence, if you go back and think about what we have spoken about the countability and uncountability of sets, every sequence is a countably infinite set. Every sequence has a cardinality exactly same as the set of natural numbers, which is called the Aleph naught, a number given by introduced by George Cantor. So, now why have I chosen these three particular sequences? I could have chosen something else. The idea to choose this particularly these three sequences has obviously a reason. So, let us to look at the nature of each of these sequence. So, let us look at the nature of this sequence, where each xn can be now written as 1 by n. So, what is the nature of this sequence? The nature of this sequence is that as I increase the value of n, the value of 1 by n is going down. It keeps on going down, but it continues to remain positive. So, 0 is a lower bound of this, right. In fact, you can show that 0 is the infimum. Now, you see the values are going down and down and down and down, and it goes towards 0. So, this kind of sequences is called convergent sequences. These kind of sequences are called convergent sequences. So, here, so there is, we can write this following language: the limit of 1 by n as n tends to infinity is equal to 0. You understand this very well, that as my value goes down. But what about this sequence? Okay, let us, it looks a little pretty strange, minus 1 plus 1 minus 1 plus 1. Let us look at this sequence. So, here my xn is equal to n square. So, what would happen? Can I say something about this? Where does the function value goes? What is the value of the sequence? Where does the value tending towards? So, here it is secured that it is tending towards 0, it is going down and down and down. Here it is going up and up and up and up and up. The more n you increase, the more n square becomes bigger and bigger and bigger, and n squared starts growing faster than n. If you look at the function y equal to x, and if you look at the function y equal to x square, and if we just draw the graph of these two, that after x equal to 1, x square starts growing faster than x. So, which means this goes to actually becomes, it blows up, and we can write that this goes to plus infinity. So, if the limit of a sequence is plus infinity, such a sequence is called divergent. So, this is an example of a divergent sequence. You might think that okay, convergent sequences are better and divergent sequences are not so good idea. Let me tell you the famous mathematician G.H. Hardy, who has actually nurtured Ramanujan in Cambridge and actually spread the word across the world of what a genius Srinivasa Ramanujan was, our own Srinivasa Ramanujan. He had a whole book called Divergent Series. So, do not think that mathematicians can play around with things which supposedly looks strange. Now, what is this series doing? Divergence. So, this is a divergence sequence. So, we have a convergence sequence, not series, sorry. This is called a divergence sequence, this is a convergence sequence. So, we understand, it is intuitively we have the feel that okay, I go to some numerical value, so I converge to that value. If I just blow up, I do not converge. If I blow up in the plus infinity sense or minus infinity sense, because I do not have any finite limit, then of course, I say it is divergent. But what about this? This sequence is very strange. It is also a divergent sequence, but of a different type. So, divergent sequences are of two types. One is the one which blows up, either goes to plus infinity or minus infinity. Another one, suppose you have put minus n square, then it would have blown to the other side. So, this sequence is called an oscillating sequence. It is diverging, it is not converging. Anything which does not converge must diverge, it is called divergent. So, it is called oscillating sequence. So, what does this great oscillating sequence does? It just goes between plus 1 and minus 1, plus 1 and minus 1. It is not blowing up to either minus infinity or blowing down to minus infinity or blowing up to plus infinity, nor under any circumstances it is moving towards a fixed number. So, such a sequence is called oscillating sequence. So, these are the three basic natures of a sequence. Now, once this is known, the three basic natures, let us try to make a more better definition of a convergent sequence. Let those examples be there, we need them very soon. So, what I mean by this statement, limit xn n goes to infinity is equal to some L. What is the meaning of this? So, that is n goes to infinity, you obviously you just keeping on increasing the value of the natural numbers. What does it mean? Again we will go to the epsilon formulation, there is no delta here by the way. What it says that when n is very large, xn is actually very near L, that is the meaning of this. So, the English statement is this: when n is large, xn is very near, of course you have to quantify what is very near L. That is the English meaning of the statement. Intuitively this is the meaning. So, when I have this meaning, how do I translate it into a mathematical language? So, I said okay, for what n I give you a distance, I say okay, choose a distance between xn and L. So, for what n you will have xn and L is there a distance less than a given epsilon which I give it to you. So, the question is so natural in that I will tell you okay, can you find an n for which xn and L is actually very near. So, I will give you what for me very near means it should be less than some epsilon. So, can you find such an n? So, if you can do that for every epsilon, then of course you are talking about a sequence being convergent. So, given epsilon greater than 0, there exists n naught element of n such that for all n bigger than equal to n naught, x n minus L, this distance, the absolute value is less than epsilon, strictly less than epsilon. That is exactly the meaning. For any given epsilon, this must be true. So, what it says that, so you come up from x1, x2 dot x n naught, after that whatever x n you take, x n the distance is less than epsilon. So, now if you change the epsilon, make it more smaller, then the n naught would be changed, maybe you have to come much more. So, what it says, n bigger than n naught means up to n naught there are only finite number of objects x1, x2 dot 1, 2, 3, 4, 5, 6, 7, 8 n naught, and after that for all the n's, which is called the tail of the sequence after n naught, it is within that limit x n minus L. We will just draw it and show you. So, what it simply says is the following, it tells you that except a finite number of, if you give me any epsilon, I can show you except a finite number of elements of the sequence members, all the other members are within that limit. So, for example, let me draw. So, suppose a sequence is said to go to L. So, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is so on. So, this is L, and then these are L plus epsilon and L minus epsilon bands. So, it is the 2 epsilon band around L, right. So, this point is L plus epsilon and this is L minus epsilon, okay. That is what it is. And now suppose you have x1 is here, this is x1, then x2 is here within this band, and then x3 is here, x4 is here, and then x5 is here, x6 is here, x7 is here, x8 is here, x9 is here, and so on. So, what is happening? So, for now our n naught here would be equal to 5. So, after 5 and from 5 and then onwards, all the xn's are within this 2 epsilon band. So, this is the 2 epsilon band. Okay. Now, we will give our first mathematical result about the nature of a sequence, but by discussing first what is called a bounded sequence. These bounded sequences plays a very major role in many things. So, it is a diagrammatic representation. So, if you look at this, draw the diagram, like just if you connect the sequences by a line, you will immediately see the nature. So, after x5 everything is within that 2 epsilon band, x5, and so that is actually a very nice way of looking at the behavior of sequences, as if you are walking down the alley. So, there is something called bounded sequences. So, a sequence from now on in short SEQ, sequence xn is bounded, which I also write in short BDD, if, so if maybe I should not do this, it will become, so sequence is bounded if there exists m greater than 0 such that, or could be 0 greater than equal to 0, does not matter. Maybe because xn could be 0, 0, 0, 0 also. That is the meaning, which simply means that xn must lie within m and minus m. that is what it simply means. Now, there is a beautiful connection between convergent sequence and bounded sequence. For example, this sequence which does not converge is bounded. So, every bounded sequence need not be converged. When you talk about bounded sequence, you immediately think that possibly okay, these are bounded by some numbers, fixed numbers, you know, the function has to be convergent, somewhere its limit cannot get out of certain things. Of course, the limit of xn would always, if there is a limit, should lie between m and minus m, but who said that there will be a limit? That is the whole point. So, every convergent sequence will become bounded, but every bounded sequence is not convergent. So, we will first start a way of proving this fact that every convergent sequence is bounded. This is one of the earliest proofs that you see in mathematical analysis, that or real analysis, that every convergent sequence is bounded. So, how do you prove that? Example that a bounded sequence is not convergent is here right at your nose on the, so here, so that is exactly why I kept on holding to these sequences. So, how do I prove this fact? So, this is what anybody, any mathematician worth its salt would call a theorem, because this is a very, very important result. So, let us start doing the proof. We will start removing some parts from here. So, we remove the first part. So, let me do the proof. So, you already have the answer of the other part. Let me do the proof. So, how do I prove this statement? A mathematician would formally write the word proof. And you see, I want to just let you know that you could say that you do calculus pretty well without even knowing all this, but does not matter to know something higher, so that you can actually do a lot with it, learn and do a lot more with it. Now, after telling you this, I will tell you something interesting, something associated with our continuous functions, where that you know, the idea of continuity can be put into the language of a sequence. Now, proof is the following. So, xn is bounded. So, right. Now, consider xn to be convergent. Let epsilon be equal to 1, then there exists n naught element of n such that for all n bigger than this n naught, mod xn minus L is less than epsilon, less than 1. Okay. This is all right. So, now take this sequence xn, just write xn. And this can be written as xn minus L plus xn minus L plus L, which can be written as now for all n bigger than equal to n naught, from this inequality, this fact, this inequality, you would have xn less than equal to, this is less than 1 just by this equation 1 plus mod L. Now take the maximum value of x1, x2, x of n naught minus 1. So, let this be m. So, from n naught onwards this is true, it is bounded by 1 plus mod L, because L is a fixed number, this is convergent, you know the limit, this is L. So, this is bounded by this number. Now, there are only finite number of them are there. So, you take those values, the finite number of parts of the sequence which you have not considered, because everything beyond that goes inside the 2 epsilon or one L 2 band, right, the band of length 2. Now, among these remaining part, the finite you have, you take the maximum one. So, for all of these are now less than equal to m. So, now find m hat which is equal to maximum between this one, this capital M, and 1 plus mod L. Just look at the thinking. So, when n is bigger than n naught, I know that the function value is less than equal to this. So, hence the function value would also be less than equal to m hat, because m hat is bigger than 1 plus L. And here I know that the function value for the remaining finite part, the function value is less than the sequence value is less than m. And mod of this, or rather, so I should rather take like this. I forgot, sorry, I just made a mistake. So, the mod of x1, x2, xn, all of these is less than m, and that m is also less than m hat. So, what I have concluded from here? I have concluded that mod of xn is less than equal to m hat, right, because m is non-negative and this is non-negative. So, m hat is non-negative for all n element of n, and lo. So, we have proved that it is bounded by the given definition. Now, what is the link between sequences and continuity? This is some important link that you should really know at this very out stage, when I have a very okay, where is this? Now, let me tell you something about the link between sequences and continuity. So, if a function is if f is continuous, say from Rn to R, just do not bother about the, then for any xn going to x, fxn must go to fx. So, this symbolism you might suddenly see why I am writing this symbolism. This is a equivalent symbolism for this. This way, if instead of writing x limit of xn is this, you can always write like this. This is a shorthand of this, shorthand. I like shorthand, it's better. So, this is what, if f is continuous, this will happen. In fact, the opposite also happen. Function f is continuous if and only if for every sequence xn this is happening. So, let us just prove this part. Let us try to you think about the other part. So, what happens if f is continuous? Now, you take any xn minus x, okay? So, what is the meaning? Given epsilon greater than 0, what is the continuity of f? What of I? Given epsilon greater than 0, there exists delta greater than 0 such that whenever so x is tending to so maybe I should write x naught maybe. So, when x is tending to x naught, that is when x minus x naught is less than delta, we have fx, it implies that fx minus fx naught is less than epsilon. Okay. Now, so given because I know that f is continuous at x naught, so given any epsilon this is true. Okay. Now, I also know that xn is going towards x naught. Now, for delta greater than equal to 0, there exists an n naught dash element of n, of course depending on the choice of this delta, such that for all n which is bigger than n naught dash, I would have xn minus x naught to be less than delta. And by this and for all such points, it will imply again by the definition of continuity that f of xn is minus f of x naught is less than epsilon. So, given the epsilon greater than 0, I have shown that there exists a n naught dash element of n such that for all n bigger than this n naught dash, f x n minus f x naught is less than epsilon. What does it imply? It simply implies that f x n goes to f x naught. You can retrace it back and come back and show that f is continuous. So, that part you can do, and this is a very basic introduction about sequences. So, tomorrow what we are going to do is we are going to learn about monotonic sequences and their behavior, increasing sequence and decreasing sequence. What is their behavior? Once we learn about these two important features of sequence, we are going to learn an important concept called limit supremum and limit infimum, and then once that is learned, we will introduce to you what is called a series, right, and that will be very important. So, tomorrow we are going to look into these facts, and which will be the starting our 8th week and the last week of our syllabus, and once we will be doing that, we will talk more about Taylor's theorem and associated things and as we go on. So, I hope we had a very basic introduction. So, let us see that what you have learned today is a way of doing proofs in mathematics, way of doing proofs in real analysis. This is very important. So, also a sequential definition of continuity, f is continuous if and only for any x n going to x naught, f x n goes to f x naught. So, I have shown that if f is continuous, then this happens. So, you can also retrace the logic back and try to see whether you can yourself try and prove that f is continuous if this happens for any sequence. So, you have to understand the word any sequence, there is a word any, it is not for some fixed sequence, it is for any sequence this will happen. Then only the function is continuous. It is slightly tricky to go back, but just try it out. Thank you.